Settle in and let the day loosen its grip on you, because down here, beneath quiet fields and ordinary roads, the air turns cool and faintly metallic. You walk through a tunnel that smells like dust, warm cables, and old paint, and you hear it, that steady, patient hum. Not dramatic, not heroic, just a machine doing its job. In the dark, you might think a particle accelerator is all sparks and spectacle. It is not. It is mostly waiting, watching needles drift, and writing careful notes in a logbook at 3 in the morning. Tonight, with the Sleepless Scientist keeping you company, you are going to take the gentle night shift at early CERN and learn how invisible particles were persuaded, softly, to behave. You arrive before dawn, when the outside world is still pretending it is asleep. Down here, the light is practical and tired. It falls in small pools across concrete floors, and it makes everything look slightly older than it is. Your shoes scuff dust that has been ground fine by years of foot traffic. The air is cool but not fresh. It carries that faint electrical smell, like a radio left on too long. There is also metal, not the sharp scent of a coin, but the dull, warm scent of steel that has been gently heated for hours, and the sound never fully stops. It is fans somewhere behind panels. It is transformers that do not sing so much as they mutter. It is the thin rattle of airflow in ducts and the occasional click of a relay deciding to be alive for another minute. You step into the early control room and your brain has to recalibrate. You were expecting something cinematic, glowing holograms, starship drama. Instead, it feels like a careful person's workshop. There are racks of electronics with small indicator lights, some confident, some uncertain. There are meters with needles that rest where they rest and shift when they feel like it. There are knobs that look like they were borrowed from a respectable stove. The real centerpiece is not a screen. It is paper. A logbook sits open, thick, and patient, with pages that smell faintly of ink and skin oil. Handwriting layers itself across the lines. Notes, times, initials. The human urge to leave a trail that says, "I was here," and the machine did not explode. You take your seat. The chair does not roll smoothly. It squeaks, just a little, the way old chairs like to remind you that comfort is always conditional. This is the job. In the early days, you do not conquer particles. You supervise them. You watch. You wait. You learn the slow language of a machine that never speaks plainly. Most minutes are quiet, not silent, just quiet. A needle drifts a fraction to the right, then returns, as if reconsidering. A light flickers once, and you make a small mark in the logbook anyway. Not because it matters necessarily, but because your whole life down here is built on noticing small changes before they become large ones. You might imagine the big drama is the beam itself, the invisible river of particles, the famous thing everyone talks about. But down here, at this hour, the biggest drama is often a power supply that runs slightly warm. A cable that smells a bit too hot, like rubber remembering it was once a tree. A stubborn switch that needs the exact right pressure, not force, patience. And patience is what you have, because the machine insists on it. You glance at the instruments again. The readings are steady enough to feel like breathing, steady enough that you begin, quietly, to wonder what all this effort is actually for. And as your eyes adjust to the dim lights and the slow rhythm of instruments, you start wondering what exactly this huge machine is trying to do. It helps to think of the accelerator not as a weapon and not as a spectacle, but as a very long argument with nature. You are trying to take something unimaginably small, a particle you will never see, and persuade it to move faster, and also, at the same time, persuade it to stay where you want it. Those two goals are not friends. If you push something to go faster, it becomes less cooperative. It gets ideas. It wanders. It becomes, in its own silent way, rebellious. So, an accelerator is a compromise machine. It is a ring or a line built out of discipline. It is designed to deliver tiny, repeated nudges while constantly correcting tiny, repeated mistakes. The particle does not know it is in your experiment. It does not care about your funding. It does not care that you stayed up all night. It responds to fields. That is all. Electric fields to push it forward. Magnetic fields to guide it sideways. You are not grabbing the particle and throwing it. You are shaping the space around it so that it has only a few choices that feel natural. The magnets are the gentle hands on the handlebar, not hands that touch, because nothing touches the beam if you can help it. Hands that guide. They bend the path quietly, the way a curved track guides a train. If you want a mental picture, imagine riding a bicycle in the dark through a long tunnel. You cannot see the walls, you can only feel the handlebar. You make small corrections constantly to stay centered. Now remove the bicycle. Remove the idea of a solid object at all. Congratulations! You are now doing it with magnetism. The electric fields are the pushes. They are timed. They have to be timed, because if you push at the wrong moment, you do not help the particle. You sabotage it, you steal energy instead of giving it. You trip it politely. The simplest way to picture it is a child on a swing. If you push at the right moment, each push adds up. The swing goes higher, not because one push was dramatic, but because many pushes were consistent. That is the accelerator's whole philosophy. No drama, just repetition accuracy, and a refusal to get bored. In the early days at CERN, this philosophy had to be built with equipment that feels, compared to modern systems, almost tenderly handmade. You look at the dials and you realize they are not decoration. Someone calibrated those. Someone wrote down what they should read and what they actually read. Someone learned that this particular dial lies when the room gets too warm. The control systems are not a single brain. They are a collection of careful habits. You check a meter. You adjust a knob a fraction. You wait. The waiting is not passive. It is listening, but with instruments. You watch how the beam responds. Indirectly, you cannot see particles. You see their effects. A rate changes, a current shifts, a detector ticks a little differently. It is like caring for a shy animal that only communicates by moving the grass. And you do all of this because if you can keep the particles moving fast and keep them on course, you can make them do something useful. You can crash them into a target or into each other and watch what comes out. That is the blunt version. The softer version is that you are asking questions with controlled accidents. You are building conditions where nature has to answer in a way you can measure. And, crucially, you are doing it in a way that is more about control than about violence. The particles are energetic, yes, but the whole machine is designed to keep them calm enough to be predictable. There is a special satisfaction in that. Not triumph, not conquest, just the quiet pleasure of a system behaving exactly as the equations promised it would, provided you treat it with respect. But guiding an invisible stream through a long ring only works if the inside of that ring is almost perfectly empty. You turn your attention, as every operator eventually does, to the part of the machine that feels the most boring and is, in practice, the most unforgiving: the vacuum. Inside the beam pipe, air is not a helpful background. Air is a crowd. Air is a swarm of molecules bouncing around with cheerful violence, hitting anything that tries to pass through. If your particle beam has to travel through that, it will not stay a beam for long. It will scatter. It will lose energy. It will collide with random molecules and produce little sprays of nonsense. It will, in the most understated way possible, fall apart. So you make the inside of the beam pipe into a place that is almost nothing. Not philosophical nothing, engineering nothing. You pump the air out, you chase down leaks, you seal flanges, you listen to the vacuum system the way a sailor listens to a hull in bad weather. In the early days, this is not a sleek process. It is practical. It is noisy. It is full of small rituals. Pumps thrum and vibrate through the floor. Valves open and close with a deliberate clunk. Gouges display numbers that you learn to read like moods. A good vacuum is not exciting. A good vacuum is a stable line on a chart that refuses to misbehave. And yet, making that near nothing is surprisingly hard, because the universe is full of matter that does not want to leave. Even if you pump out the air, the inside surfaces of the pipe hold on to molecules. Water clings, oils cling. Gases hide in tiny imperfections of metal, tucked into microscopic valleys like campers who refuse to pack up. So you do something that sounds almost like a myth until you have done it yourself. You bake the vacuum chamber. You gently heat the metal so those trapped molecules gain enough energy to let go. They drift into the vacuum where the pumps can catch them and remove them. It is slow. It is careful. It makes the entire system feel like you are coaxing a haunted house to exhale. The smell changes when you do this. Not dramatically, but enough. Warm metal has its own scent, and old seals, when warmed, have a faint odor of rubber and time. Cleanliness down here is not shiny. It is not sterile white. It is hands in gloves wiping down surfaces. It is solvents. It is lint-free cloths. It is someone, at some point, deciding that a single fingerprint on the wrong flange is a small tragedy. Because inside the beam pipe, every stray molecule is a potential collision, not a cinematic collision, a tiny, quiet one. But the beam is delicate. It is a disciplined stream of charged particles. It cannot afford too much chaos. So you stare at a vacuum gauge, and you learn to love the feeling of the number slowly, slowly improving. It is one of the most calming things in the whole operation, if you let it be. The emptier it gets, the quieter the beam becomes, like a thought that can finally hold still long enough to finish itself. Of course, the machine does not always cooperate. A seal can leak. A gasket can be imperfect. A flange can be tightened with just slightly the wrong pattern of bolts, creating a tiny unevenness. And that tiny unevenness becomes an invitation for air to creep back in. Leak hunting in an accelerator is not heroic. It is detective work conducted at the speed of boredom. You listen for changes. You spray a harmless tracer gas near suspicious joints and watch how the gauges respond. You check connections the way someone checks doors before bed, one after another, wanting reassurance. Sometimes you find the leak quickly and you feel briefly competent. Sometimes you do not, and you realize you are in a relationship with a machine that enjoys making you earn your rest. The strange part is that the deeper the vacuum gets, the more the remaining problems begin to feel subtle. At ordinary pressures, gas behaves like something you can ignore. At very low pressures, every molecule that remains feels personal. You become aware of outgassing, the slow release of gas from materials. You learn that not all metals are equal. You learn that some plastics are basically air sponges. You learn, slowly, why accelerator engineers can talk for an hour about the virtues of a particular seal, because their job is to make a long tunnel of metal behave like outer space while sitting under a calm European countryside. And once you have made a place that's nearly nothing, you can finally try to put something delicate into it and keep it there. This is where the magnets come back, lined up along the ring like a repeating lullaby. Each magnet has a job. Some bend the beam around curves. Some focus it, squeezing it inward so it does not spread. Some correct small errors, nudging it back toward the center when it drifts. It is not one big magnet doing one big thing. It is an ecosystem of magnets doing small things in careful sequence, like a chorus that keeps time by never missing a beat. In the early days, you do not just press a button and trust the software. You are the software. You turn knobs, you set currents, you watch readings, you wait for the beam to respond. Then you adjust again. There is a particular kind of fatigue that comes from this. Not the fatigue of running. The fatigue of attention. Tiny changes matter. A fraction of a turn on a control can move the beam's path, not visibly, but measurably. You learn to make the smallest adjustment you can manage, then stop, then wait. Waiting is part of the adjustment, because the machine has delays. Components warm up, currents settle, magnetic fields stabilize. The system is not instantaneous, and if you chase every twitch, you will create oscillations. You will make the machine seasick, so you develop a calm style. You touch a control, you pause, you observe. If you do it well, the whole control room feels like someone tuning an instrument very slowly in a quiet house. Power supplies matter here as much as the beam physics, and sometimes more. A magnet is only as steady as the current running through it. If the current wobbles, the field wobbles. If the field wobbles, the beam wanders. And the beam does not wander in a friendly way. It wanders like a cat deciding it no longer lives with you. So you watch the power supplies like you watch weather. Are they running warm tonight? Are they humming differently? Is one of them making a slightly irritated sound, the way a fan does when dust builds up? You learn the truth that every early operator learns. The beam is not a hero. The beam is skittish. It will vanish without apology. And when it vanishes, it rarely does so with a bang. It disappears with a quiet flattening of a line, a count rate that drops, a signal that fades and leaves you staring at the instruments as if they have betrayed you. You do not shout. Nobody shouts. It is too late at night for that. And also, shouting does not bring particles back. You make a note. You check the last stable readings. You start stepping backward through the chain of cause and effect. Was the vacuum steady? Were the magnets steady? Did the timing drift? Did a component warm up and shift just enough to matter? Early accelerator work is full of this gentle, relentless troubleshooting. And part of the strange comfort of it is that the causes are often mundane. A temperature change can alter the resistance of a circuit. That changes a current. That changes a magnetic field. That changes the beam orbit. That loses the beam. The universe, it turns out, does not always require dramatic villains. Sometimes it just requires a room that got a little warmer because someone opened a door. You glance at a thermometer on a panel and you do not laugh, but you could. All this sophistication, and you are still, in some ways, at the mercy of warm air. So you build habits to protect against those small indignities. You keep the room stable. You monitor cooling water. You listen to pumps. You learn which knobs are safe and which ones are cursed. Cursed knobs are a real phenomenon, not because of magic, but because of history. Someone once turned that knob too far and lost the beam for 6 hours. Now everyone approaches it with respect. They touch it like it might bite. Knowledge spreads down here the way it spreads among people who share a difficult job. Quietly. Through stories. Through warnings. Through small jokes that are mostly exhaustion wearing a mask. You take another look at the instrument panel and you notice something that could be nothing or could be the beginning of your next hour. A needle is not where it was, not dramatically, just not quite. So you do what operators do. You confirm it. You check a second instrument. You check a third. You treat your own perception as suspect until the machine agrees with you. Then, carefully, you make a small adjustment, a fraction of a turn. You wait. The needle returns, slowly, like an animal deciding the room is safe again. You write it down. Time, change, result. Your handwriting is neater than it feels. In this way, the night passes, not in big scenes, but in small loops of attention, and you begin to understand something that people rarely say out loud about accelerators. The machine is not just physics, it is routine. Routine is what turns impossible precision into something repeatable. Routine is what allows a beam of particles, smaller than dust, to behave as if it understands schedules. It does not understand, of course. It merely obeys the fields you create. But your routine is part of the field in a way. Your habits create stability. You check the same gauges in the same order. You listen for the same sounds. You make the same notes. You do not skip steps, even when you feel tempted, because the machine punishes improvisation, not out of spite, out of indifference. It is simply sensitive, and you are simply human, and the relationship works best when you respect both of those facts. Speaking of sensitivity, there is something else you learn quickly. Once you have coaxed a beam into existence and tried to keep it alive. The beam does not announce trouble loudly. When things go wrong, they go quiet first. And that is where your real work begins, in the small, soft signs that something is slipping. It starts with a softness you almost miss, a detector count that is a little less enthusiastic, like rain easing off on a roof. A chart recorder pen that used to scratch a confident line, now drawing something flatter, lazier. You do not get an alarm. Not yet. You get a mood. The beam, when it is healthy, has a kind of presence, not visible, but implied, in the way several instruments agree with each other. A steady circulating current, a predictable splash of signals where the beam brushes a monitor, a gentle hum of numbers that makes you think, yes, the invisible thing is still there. When it starts to fail, it does not scream, it sulks. You lean closer to the panel, not because it helps, but because humans lean toward trouble. Your eyes move in a practiced loop. Beam current, magnet current, radio frequency voltage, vacuum pressure, temperature, cooling water flow. You do it in the same order every time because the order keeps you from lying to yourself. And the funny thing is, most of the time, the machine is not broken. It is simply drifting. That is the first lesson of an early accelerator shift. The universe loves a slow drift. A resistor warms, its value changes, and the timing slides by a whisper. A magnet power supply ages, and the ripple in its current grows just enough to matter. A cooling line carries water that is a few degrees warmer tonight, and a cavity frequency shifts like a singer going slightly sharp. You are not fighting a monster. You are fighting the gentle tendency of everything to stop being perfect. So, you do what an operator does. You confirm, and you narrow. You look for correlation, the way a tired brain looks for meaning. Did the beam current start dropping when the temperature rose? Did the vacuum gauge twitch before the detector count softened? Did someone, hours ago, adjust a knob and forget to write it down because they were human and it was late? Congratulations, you are now doing forensics on an invisible thread, using needles and hums. Sometimes the culprit is embarrassingly simple. A timing trigger is misset. In an accelerator, timing is not a convenience. Timing is the whole religion. The radio frequency system has to push the beam at the right moment, again and again, like catching your foot on a stair you cannot see. If the phase is off, the particles stop gaining energy smoothly. They begin to spread out, to slip, to lose their neat bunching. A bunched beam is a disciplined crowd. An unbunched beam is a crowd leaving a stadium through a narrow door. The door, of course, is your aperture, the tight physical space inside the vacuum pipe. If the beam spreads, it scrapes. If it scrapes, it sheds particles into the walls. If it sheds enough, your instruments grow quiet, and you can almost imagine the beam, offended, dissolving into the metal like a secret. You make a small adjustment to the timing, a fraction. You wait. You watch the beam monitor respond. Sometimes the beam comes back like it only stepped out for a cigarette. Sometimes it does not. When it does not, you go down the list. You check the magnet currents, because magnet stability is a kind of bedtime story down here. The dipoles, the ones that bend the beam around the ring, must be steady. The quadrupoles, the ones that focus the beam, must be steady in a more subtle way. The beam is not just a line you steer. It is a moving, vibrating bundle, a swarm of charged particles trying to spread from mutual repulsion. The focusing magnets squeeze that swarm back into shape, the way a careful hand guides a loose bundle of wires into a neat cable tie. If the focusing is too weak, the beam grows fat and lazy and hits the wall. If the focusing is too strong, the beam can oscillate like a plucked string and still hit the wall. The beam is talented like that. It finds a way. So you look at the tune, the Betatron tune, the number that tells you how many oscillations the beam makes per turn. In the early days, you do not always see it as a clean digital readout. You infer it. You measure it with instruments that feel like they are translating from a language nobody speaks at home. And if that tune drifts toward a resonance, you get a new kind of quiet. Resonance is the machine finding its own worst habits. It is the beam's oscillations lining up with imperfections in the magnetic field. Every turn adds a little shove in the wrong direction, and the beam grows more confident in its mistake. It is like pushing a shopping cart with one bad wheel. At first, it is manageable. Then, if you keep pushing the same way, it starts to pull harder and harder until you are fighting it with both hands. You have seen this before, and that matters. Experience in a control room is mostly memory, not of facts, but of feelings. You remember that one power supply that drifts when it is warm. You remember that one magnet that hums differently when the ripple grows. You remember the gauge that tells the truth and the gauge that tells what it wishes were true. So you sit there in the low light, listening to electricity, and you do not panic. Panic is loud, and the machine is quiet. Loud emotions do not help with quiet clues. When you do have to act, you do it gently. You nudge a correction magnet, one of the small steering elements that can shift the orbit without changing the whole lattice. You watch the beam position monitor, the little device that can tell you if the beam is centered. In early systems, that readout may be crude, but it is enough. Enough to say, yes, you are drifting left. Enough to say, no, you are now scraping. You learn to love the word scraping because it is honest. When particles hit the wall, they make secondary showers. They can produce radiation that your monitors see as a rise in background. They can heat a spot. They can desorb gas from the wall, knocking loose molecules that were politely stuck there. That gas worsens the vacuum. Worse vacuum means more scattering. More scattering means more loss. This is how a beam can die from embarrassment. It touches the wall exhales, the vacuum degrades, and the beam collapses in a feedback loop that feels almost emotional. And if you catch it early, you can stop the loop. You correct the orbit. You stabilize the vacuum. You wait, because time is an active ingredient in accelerator work. The pumps pull down the gas again. The surfaces resettle. The machine forgives if you are careful. But sometimes, the beam is simply gone. The chart line is flat, and the quiet has won. That is when the night shift becomes an exercise in rebuilding a fragile thing from the beginning. First, you return to injection. In many early machines, you have a chain of accelerators feeding each other like a set of nesting dolls. A small injector, a booster, then the main ring. You cannot just conjure a beam in the big ring. You have to prepare it. So you check the injector conditions. Ion source stable, extraction timing right, beam transport line magnets set. The little beam must arrive at the big ring in the correct shape, at the correct time, with the correct energy, like a train arriving at a platform where the doors must line up exactly. You verify the kicker magnets, the fast pulsed magnets that nudge the injected beam onto the correct orbit. They have to fire at just the right moment. Too early, or too late, and you kick nothing, or you kick the wrong thing. You can send your beam into the wall with the efficiency of a bureaucrat stamping the wrong form. You check the pulse-forming network, the thyrotron, the components that feel more like a radio transmitter than a physics experiment. In those early rooms, you can smell the insulation warming. You can hear the faint click that says, yes, the pulse happened. And you look for the simplest evidence of success. A blip on a beam transformer. A brief rise in a signal that says, something made it around. At least once. Sometimes it only makes it around once. A circulating beam is not guaranteed by injection. It is earned. If it dies after one turn, the orbit is wrong, or the focusing is wrong, or the aperture is too tight somewhere, or you have a piece of hardware that is shifted by a hair. A millimeter matters. Less than a millimeter matters. The strange comfort is that the beam's failure is information. If it dies instantly, your problem is likely gross. If it survives a little, your problem is likely subtle. If it survives for minutes, then dies slowly, your problem may be thermal, or vacuum, or timing drift. So you become a kind of translator. The beam cannot speak, but it can fail in different dialects. And because the machine is indifferent, it will teach you as many times as you need. You make notes as you go, because memory is fragile at 3 in the morning. You write down the magnet settings, the times, the small interventions. You record what happened, even if it feels like nothing, especially if it feels like nothing. Because later in daylight, someone will ask, when did the drift start? And you will want to answer with ink instead of guesses. There is a particular style of communication that grows in these rooms. It is not dramatic. It is procedural and calm, like a nurse's handover. You write for the next shift as if they are you, but less tired. You explain what you saw, what you tried, what worked, what did not. You leave breadcrumbs in the logbook because the machine is a maze and you are all taking turns walking it. And sometimes the maze is not technical at all. Sometimes the beam disappears because someone in the building flipped the wrong breaker, or a power glitch rippled through the grid outside, or a cooling pump tripped on a float switch that stuck. Early accelerator operations are full of these humiliations. You can have brilliant beam physics and still lose the beam because a relay decided it was done with this century. So you learn to respect the infrastructure, the power distribution, the cooling plant, the ventilation, the water quality, the mundane systems that keep the glamorous systems from melting. You learn that a particle accelerator is not one machine. It is a city of machines. And cities have plumbing. Speaking of plumbing, you start noticing how much water is involved in a device that seems, at first glance, all vacuum and electricity. Cooling water runs through magnets and power supplies. Heat exchangers breathe quietly somewhere behind doors. Pipes sweat. Valves stick. Water is the soft, persistent enemy of electronics, and also their only friend. And when cooling goes wrong, the accelerator does not burst into flames. It simply becomes unreliable. A magnet warms. Its field drifts. A power supply warms. Its regulation worsens. The beam starts to scrape. The vacuum starts to degrade. And again, you get that first sign, not a bang, but a quiet. So you walk sometimes out of the control room. You take the long corridor, past panels and warning signs and doors with heavy handles. The tunnel air feels cooler here and carries more dust. You can hear the accelerator in pieces. localized sounds. A pump here, a transformer there, a distant fan with a tired bearing. In older installations, the lighting is not flattering. It makes every surface look like it has been through something, which is fair. You find the cooling rack and you listen, because you can hear water problems if you have learned the language. A healthy flow has a steady hiss. A partial blockage has a higher pitch, a strained sound, like breathing through a narrow straw. A pump cavitating sounds like gravel. You touch a pipe carefully, warm is fine. Hot is a story. Hot is a chapter that ends with someone calling maintenance. You check for leaks, not because a drip will drown you, but because water, where it should not be, becomes corrosion. And corrosion becomes resistance. And resistance becomes heat. And heat becomes drift. And drift becomes quiet. Everything is connected by small, boring pathways. You return to the control room, and the instruments look slightly different now, as if they noticed you left. You sit again. You adjust again. You wait again. And if you are lucky, the beam returns. The count rate rises. The chart pen draws a more confident line. The room's mood improves by a fraction. You do not celebrate. You just continue. Because the early days are not about constant discovery. They are about learning how to make the machine stable enough that discovery becomes possible. Eventually, after enough nights like this, you start to anticipate trouble before it arrives. You recognize the pre-quiet, the subtle flattening that comes before a trip. You notice a power supply starting to hum differently. You see a vacuum gauge that creeps so slowly it would be easy to ignore. And you do not ignore it. You take preventive action. You adjust the orbit slightly so the beam is more centered through a known tight spot. You reduce the intensity, sacrificing some performance to gain stability. You tweak the radio frequency voltage, giving the beam a firmer bucket, a stronger confinement in phase space. Phase space is one of those terms that sounds like science fiction, but it is simply a bookkeeping trick. It is how you describe not just where the particles are, but how fast they are changing. Position and momentum together as a shape. A good beam is a small shape. A bad beam is a smeared one. So you keep the shape small, and you do it with fields and patience. The longer you sit with these systems, the more you realize that accelerator operation is not mostly about speed. It is about boundaries. The beam lives in a narrow corridor of allowed conditions. Too much gas, it scatters. Too little focusing, it expands. Too much focusing, it resonates. Too much energy spread, it debunches. Too much intensity, it wakes up collective effects. The beam interacting with its own electromagnetic fields and with the impedance of the machine. Yes, the beam can argue with itself. At higher intensities, the beam is not just a passenger, it becomes a source. It excites wake fields, little electromagnetic echoes in the structures it passes, like a boat making a wake in a canal. Those wakes can push on the beam behind, destabilizing it, creating oscillations that grow. In early days, you might not push intensity far enough for the worst of these effects, but you still taste the beginning. A beam that seems fine until you increase current, then suddenly becomes jittery. A signal that gets noisier as you try to do better. Nature's favorite joke is that improvement creates new problems. So your job tonight is to keep everything within the corridor, to keep the beam alive long enough that the people upstairs the ones waiting for data, can take their measurements, and that is the point where the work changes flavor. Because at some hour, after enough stable turns, after enough quiet corrections, the machine is not just running. It is ready for the part that looks like science from the outside. Not the maintenance of invisibility, but the extraction of meaning. You glance at the schedule, written in pen, because ink is more reliable than ambition. There is a planned run, a target, a detector setup, a measurement that needs stable beam conditions for hours. The beam is no longer just a beam. It is a tool, and tools have to be gentle if you want them to tell you the truth. So you shift your attention toward the devices that sit at the edge of the beam's path, waiting for the rare moments when something interesting happens. Detectors. The word sounds modern, but the early reality is tactile. Wires, gas, scintillators that flash, photomultipliers that turn faint light into electrical pulses, cabinets full of discriminators and coincidence circuits, logic built from hardware that clicks and warms. A detector is a translator, and like all translators, it has opinions. It can miss things. It can count noise as signal. It can saturate if you give it too much. It can drift with temperature. It can lie politely unless you calibrate it. So the first thing you learn about seeing particles is that you do not see particles. You see traces. A charged particle passes through a gas and it knocks electrons free, ionizing the atoms. Those electrons drift in an electric field collected by a wire, creating a pulse. Or the particle passes through a scintillator and the material emits a tiny flash of light, a little blue-green whisper, and a photomultiplier tube amplifies it into a measurable electrical signal. The photomultiplier is one of the most charmingly brutal devices in the lab. A single photon hits a photocathode, ejects an electron. That electron hits a dynode, ejects more electrons, cascade after cascade, until a single faint event becomes a pulse you can route through a cable. It is amplification by organized violence. You sit near a rack of electronics and hear a faint ticking sometimes, the sound of pulses turned into audible clicks for monitoring. It is not the particles making sound. It is the lab making sound for you, because humans trust their ears when their eyes are tired. So you listen to the universe, translated into a gentle tick, 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 like a metronome that does not care about music. In the early era, data collection feels physical. There are oscilloscopes with green lines that bloom and fade. There are strip chart recorders that drag paper under ink pens, the motion steady, the ink line a living record of a run. There are counters that click upward. There are stacks of paper printouts with holes on the sides, the kind that tear if you pull too fast. You hold a sheet, and it is warm from the printer, and you realize that this is what knowledge looks like at first. Not a revelation, a smudge of ink, and a column of numbers. Most discoveries begin as modest patterns that refuse to go away. A bump in a distribution, a coincidence rate slightly above background, a change that repeats when you repeat the conditions, which is the only kind of miracle science accepts. So you help the machine stay stable, because stability is what turns coincidence into evidence. Inside the detector, much of the work is about timing. Particles are fast, signals are fast, noise is everywhere. So the detector system often uses coincidence logic. You only count an event if 2 or 3 detectors fire within a narrow time window, suggesting a real particle passed through, not random electrical noise. In hardware, this can be a coincidence unit, circuits that take pulses and decide, with cold logic, whether they arrived together. Together means within nanoseconds, which is an absurd concept until you remember that light travels about a foot in a nanosecond. A cable length matters. A connector matters. You can change timing by rerouting a cable. So, in early control rooms and experimental halls, people are forever adjusting delays, adding cable, removing cable, calibrating timing, like musicians tuning instruments that nobody hears directly. And while you do this, you also have to know what you are counting, because a detector counts whatever triggers it. It does not know what matters. If you are looking for a rare interaction, most of what you see is background, cosmic rays from space that pass through your apparatus, indifferent to your schedule. Natural radioactivity in the concrete, noise pulses from electronics, beam-related background from stray particles hitting upstream components. So you measure background carefully. You take runs with beam off to see what the world does without your accelerator. You take runs with target out to see what the beam does when it is not interacting the way you want. You build subtraction into your thinking, and you do all of this in a space that is not glamorous. Experimental areas can smell like oil and ozone and cold metal. They are full of cables, taped down or bundled, labeled in handwriting. There are trip hazards everywhere, and the lighting is either too bright or not bright enough. There is a low-level anxiety around high voltage. Photomultipliers need it. So do wire chambers. High voltage supplies sit in racks with warning labels, and you learn the correct fear, not panic, but respect. Congratulations! Your detector is working, and it is powered by enough voltage to remind you that your body is mostly salt water. So you keep one hand behind your back sometimes, a habit borrowed from electricians, so you do not make a path across your chest. You check grounds. You check interlocks. You keep things safe because you would like to go home with the same number of functioning fingers. When everything is set, the run begins. In the control room, you see the beam status. You see the detector rates. You see the slow accumulation of data, like snow gathering on a quiet road. And the strange comfort is that the universe is consistent. Not kind, not fair, but consistent. A charged particle in a magnetic field bends the same way every time, if the field is stable. An interaction cross-section stays the same if the energy is the same. A decay time remains itself, indifferent to who is watching. Consistency is what makes measurement possible, and measurement is what makes knowledge more than a story. You might think this would feel triumphant. It does not in the moment. It feels like careful housekeeping with occasional moments of quiet satisfaction when a plot looks the way it should. In the early days, a lot of the analysis is done by hand, or at least with more hands than you would like. People measure bubble chamber photographs with rulers and templates. They count tracks. They estimate curvature. They feed numbers into calculators that are slow and loud. A bubble chamber, if you have never met one, is one of the more poetic devices in particle physics, and also one of the more ridiculous. It is a vessel filled with a liquid kept just on the edge of boiling. You drop the pressure suddenly, and the liquid becomes superheated ready to form bubbles. When a charged particle passes through, it ionizes the liquid along its path, providing nucleation points. Tiny bubbles form along the track. Then you take a photograph. So you literally photograph the passage of something that is not supposed to be photographable. The tracks curve in a magnetic field, and from that curvature, you infer momentum. The density of bubbles tells you something about energy loss. Interactions appear as sudden kinks, branches, sprays. It is beautiful, but it is also slow. Each photograph is a small book you have to read with tired eyes, and it produces mountains of data in the form of images, which then become measurements, which then become tables, which then become plots. So while you sit on shift, you are part of a pipeline that turns invisible events into physical artifacts: ink, paper, film, stacks of folders. The lab is full of these objects. Knowledge as clutter. And because it is clutter, it requires people. And people require routines. And routines require coffee. At some point in the night, someone brings a cup to your desk. It is not good coffee. It is functional coffee. It tastes like heat and bitterness and the faint hope of being awake. The cup is stained because lab cups are immortal. They have survived countless nights and countless conversations in multiple languages. The control room is a small society. You hear French, English, German, Italian, and the universal language of sighing at a misbehaving instrument. You hear someone tell a story that begins with, "Last winter, it did this." You hear someone else respond, "Do not trust that gauge after midnight." These are not jokes, exactly. They are compressed experience. In early CERN, collaboration is not an abstract ideal. It is a survival mechanism. No one person can know every subsystem. The Accelerator itself is an orchestra of specialties. Vacuum experts, magnet experts, radio frequency experts, instrumentation experts, detector physicists, engineers who know the cooling system like they know their own kitchens. So you rely on each other. When something strange happens, you do not perform a solo. You make a call. A phone on the wall, heavy and reliable, rings someone's apartment at an unholy hour. A tired voice answers. You describe the symptoms. They ask for readings. You read them out, one by one, the way a nurse reads vitals. There is a ritual to it, and the ritual keeps everyone calm because the machine does not reward panic, and neither does the person you woke up. Sometimes the expert arrives in person, hair not fully committed to being combed, eyes half awake. They stand behind you, leaning over your shoulder, and in 10 seconds, they notice what you missed, not because you are incompetent, but because they have a map in their head you do not have. They know which knob is cursed. They know which connector works loose when the humidity changes. They know that the symptom you are seeing is the beginning of a known failure mode, the kind that ends with a fuse and a smell. So you learn by watching them. They point without drama. They suggest a test. They ask you to change one thing and only one thing. Then observe. They are disciplined in their troubleshooting. They do not guess wildly. They narrow, and you adopt that discipline because it is effective and because the night is long. There is also a quiet pride in this work, but it is not loud pride. No one down here thinks they are saving the world tonight. They are saving a run. They are keeping a beam alive. They are making the conditions stable enough that someone can trust the data. If a plot looks good in the morning, it will be because of hundreds of small, boring acts done correctly at night. That is the real romance of it, if you are the kind of person who finds romance in competence. And you are, tonight, because you are here. You sit with the team and you start to notice the social physics. There is an unspoken agreement that you do not make the night harder than it has to be. You do not slam drawers. You do not argue loudly. You do not posture. The machine does not care about your ego, and your colleagues do not want to manage it. So humor, when it appears, is dry. Someone points at a stubborn control and says, "It is a delicate instrument. It requires gentle persuasion." Someone else replies, "That gentle persuasion looks suspiciously like hitting it, but softly." Nobody actually hits it because you do not hit expensive things unless you enjoy paperwork. You share small victories: beam recovered, vacuum stable, trip understood. You share small defeats: beam lost again, fault not found, gauge unreliable. You write it all down, and you eat the kind of food that exists only in laboratories and night shifts. Biscuits that taste like sugar and fatigue, sandwiches wrapped too tightly, something someone brought from home that tastes better than it should, simply because it was made by a human with daylight in their eyes. Over time, these rituals become part of the machine's operation, not officially, but functionally. The machine runs on electricity and physics. The lab runs on routine and people are wonderfully inconsistent. Someone always has a superstition. They always touch a panel before injection. They always do the checks in a certain order. They always refuse to say a certain word because last time they did, the beam dumped. You do not argue with this. Superstition is a way of coping with complex systems that are sensitive and indifferent. It is a small illusion of control that harms nothing most of the time. And if it keeps the operator calm, it is practically an engineering feature. As the hours pass, the run either stabilizes or it becomes one of those nights that teaches you something through suffering. If it stabilizes, you fall into the rhythm. Check readings, note time, adjust small drifts, confirm stability, drink coffee, answer a question from someone in the experimental area, confirm a setting, acknowledge a phone call, make a note. You become part of the background hum, and that is when the real purpose of the whole machine begins to show itself, not as a cinematic explosion, but as a slow accumulation of certainty. A detector count that stays steady? A rate that matches expectation? A plot that shows a shape you have been told should exist? You remember, vaguely, the names attached to these shapes: resonances, cross-sections, scattering angles. You remember that the goal is to understand the structure of matter, to probe forces, to see what happens when you push particles into each other at carefully chosen energies. But in the moment, it is simpler. In the moment, the goal is to keep conditions stable enough that the universe's answer is not smeared by your own noise. Because the universe already has enough noise. And the more you do this, the more you appreciate how strangely gentle a particle accelerator can be. Yes, it can make beams with energies that sound violent, but the beam itself is a thin, disciplined thread. The machine is designed to protect that thread, to keep it from touching anything, to keep it coherent. It is not a cannon. It is a violin string, stretched tight, vibrating invisibly. and always one mistake away from silence. Now, somewhere above you, the world is beginning to wake. Cars will appear on roads. Birds will do what they do, loudly, for no reason. People will complain about meetings. Down here, you remain in the night, and it is in that contrast that you start thinking about scale. Early CERN is already large, already ambitious, but it is also, compared to what comes later, almost intimate. The rings are smaller, the energies are lower, the systems are more manual. The control room feels like a place where one person's attention can matter directly. You can trace cause and effect with your own hands. As time goes on, accelerators grow because curiosity is greedy. To reach higher energies, you need larger rings, stronger magnets, or both. If you want to bend a more energetic particle in the same radius, you need more magnetic field. If your magnets cannot get stronger, you make the radius bigger. So you dig longer tunnels. You build bigger rings. You make magnets that push closer to material limits. In the early days, magnets are iron-dominated, warm, heavy, powered by large currents. Later, superconducting magnets arrive, colder than winter, carrying enormous currents without resistance, as long as you keep them bathed in liquid helium. Superconductivity is one of nature's stranger favors. Certain materials, when cold enough, lose electrical resistance entirely. Current can flow without heating, without loss. It sounds like magic, but it is quantum mechanics being practical, and it comes with a condition. You must keep the material cold, very cold. So later accelerators become not just machines of vacuum and magnetism, but machines of cryogenics, pipes of liquid helium, insulation, vacuum jackets, cold masses, quench protection systems. Because when a superconducting magnet stops superconducting suddenly, the stored energy has to go somewhere, and it often goes into heat, fast. A quench is the superconducting magnet's way of saying it is done pretending. In those bigger machines, an entire new set of night shift rituals emerges, monitoring temperatures that are only a few degrees above absolute zero, listening for the signs of trouble in pressure relief systems, watching for the kind of drift that can turn cold stability into a sudden event. But the feeling, strangely, remains familiar. You still watch needles. You still watch lines on charts. You still make small corrections. You still learn the sound of healthy systems and the sound of systems that are about to make you fill out forms. Upgrades, when they happen, are rarely dramatic in the moment. They are planned, installed, tested, calibrated. They arrive as new racks, new cables, new panels. The control room changes slowly, like a room being renovated, one wall at a time. Better electronics mean steadier power supplies. Better vacuum practices mean cleaner pipes, lower pressures, less scattering. Better beam diagnostics mean you can see the beam's behavior earlier, before it becomes failure, so the machine becomes smoother. Not perfect, never, but smoother. And the wonderful, mildly depressing truth is that this smoothness is built out of decades of people being annoyed by the same problems and deciding, finally, to fix them properly. Progress is just irritation with a budget. As machines scale up, the human side scales too. Teams become larger, shifts become more structured, documentation becomes thicker, Procedures become formal because the system becomes too complex to run on folklore alone. And yet, folklore never fully dies. Even in the biggest control rooms, you still hear someone say, "Do not touch that. It always trips." You still see someone tap a panel as if it can hear them. You still find coffee rings on printed procedures because humans cannot help leaving evidence of their presence. In the end, the Accelerator is always a collaboration between precision engineering and human imperfection. And because you are human, you start, inevitably, to ask the softer question, what are these particles really that you spend nights shepherding through a ring? You have been treating them like a beam, like a current, like a signal. But the objects themselves, the protons, the electrons, the ions, are strange little citizens. They are not tiny marbles. If you learned that picture in school, you learned a fairy tale. A useful fairy tale, like telling a child that money comes from a machine in the wall. The truth is more slippery and also, in a way, calmer. A particle in an accelerator behaves like something with a position and momentum, enough that magnets can guide it. But it also behaves like a wave, enough that you can talk about phase, coherence, and interference. This is not because the particle is confused. It is because your categories are. Quantum mechanics does not give you a solid object with a definite path, not in the way your instincts want. It gives you a probability distribution, a set of likelihoods. When you measure, you get an outcome, a definite event. But between measurements, the particle is described by a wave function, a mathematical object that encodes probabilities. Wave function is a word that sounds like an excuse, and in some ways, it is the best excuse we have that still predicts reality correctly. In accelerators, you often treat the beam as a classical object, because with so many particles, averages behave nicely. But deep down, each particle is still a quantum creature. It has a de Broglie wavelength, a wave character tied to its momentum. At high energies, the wavelength is tiny, making the particle's wave behavior harder to notice in everyday beam steering. But it is still there, like a personality trait hidden under a uniform. When you collide particles, quantum rules decide what outcomes are allowed. Conservation laws hold, not because someone enforces them, but because the universe is built that way. Energy, momentum, charge, baryon number, and many interactions, these are the bookkeeping rules reality refuses to break. And the accelerator is a way of making the bookkeeping visible. You raise energy so new processes become possible. You create conditions where rare interactions happen often enough to see. You clean up the environment so the outcomes are not drowned in randomness you did not ask for. You do not force particles to reveal secrets. You simply give them fewer places to hide. You might find it comforting in a late-night control room that the universe is consistent at this level. It does not play favorites. It does not get tired. It does not care that your shift is long. It produces the same distributions again and again as long as you hold conditions steady. And that steadiness is why you are here, watching the hum, making small corrections, keeping the vacuum deep, keeping the magnet stable, keeping the timing aligned. Because without that, the quantum world remains a blur. The longer you work with beams, the more you appreciate that probability is not the enemy of knowledge. It is the medium. A single event is just an anecdote. 10 events are a rumor. A million events are a distribution you can trust. So the lab is built to gather not one beautiful moment, but countless ordinary ones. This is why the data feels boring in the moment. It is repetitive by design. Repetition is how you turn randomness into structure. In the early days, you can feel this physically in the way paper accumulates. Sheets stack, film canisters fill, logbooks thicken. The archive grows, heavy with the weight of things that happened the same way more than once. And every now and then, amid the sameness, you see a small defiance. A bump where there should be no bump. A tail in a distribution. A rate higher than predicted. A discrepancy. These are the moments people remember later, but they do not feel like lightning in real time. They feel like suspicion. You look again. You repeat the run. You check calibration. You doubt yourself. You doubt the detector. You look for mundane explanations first, because mundane explanations are common, and ego is not a measurement device. Only after exhausting the boring possibilities do you allow the interesting one. That is how science stays sane, mostly, and even then, it takes time. Which brings you back to the rhythm of the night shift and the sense that this work is not a single story, but a long chain of careful nights. The people around you are part of the instrument, and the instrument is part of the people. Someone brings a new set of plots from the experimental area. They lay them on the table like cards in a quiet game. You lean in, and the paper smells faintly of warm toner. The plot shows a distribution, a hill of counts versus some variable, perhaps momentum, perhaps angle, perhaps invariant mass if someone is feeling ambitious. There is a small rise, a feature. It might be real, it might be noise, it might be a miscalibration, but it is something. And because it is something, you feel the room tighten. Gently, not excitement, exactly. Attention. Someone asks about beam stability during that period. You flip back through the logbook and answer with times and notes. You can point to a small correction you made. You can point to a period of steady operation. This is the hidden power of routine. It makes the data trustworthy. If the beam was stable, the detector was stable, and the feature repeats, then the universe may be whispering a new detail. If not, it is a lab artifact, and the universe remains unimpressed. Either way, you proceed the same way, calmly, repeatably, with patience, because the machine will still be here tomorrow night and the night after. And eventually, as the lab grows, the rings grow, the energies climb, the procedures formalize, and the control rooms become more modern, more digital, more screen-filled. But the core feeling stays stubbornly similar. You are still sitting in low light, listening to systems breathe, trying to keep an invisible thread alive long enough to ask reality a clean question. And reality, indifferent and reliable, will answer only in statistics. You glance at the beam readout again, because habit is comfort. It is stable. The vacuum is steady. The magnetic currents are quiet, so you let your mind drift just a little toward the particles themselves and the soft weirdness of what you are actually steering. You are guiding protons, perhaps, little bundles of quarks held together by gluons, a roiling internal storm that you ignore because the proton behaves like a unit for most of your purposes. You treat it as a point charge with mass because that approximation works, until you hit it hard enough to reveal its insides. And the entire point of high-energy physics is, eventually, to hit it hard enough. Not out of cruelty, out of curiosity. When you accelerate a proton to high energy, you are not making the proton older or wiser. You are making its wavelength smaller, making it a sharper probe, like using a finer needle to feel the weave of fabric. At low energies, you see the proton as a blob. At higher energies, you see structure. You see that it is not elementary. You see partons, quarks, gluons, momentum fractions, a probability soup of constituents. The proton becomes less like a marble and more like a bag of angry bees. And the accelerator lets you choose how angry you may not be, running at the energies where the deepest structure becomes clear. Not in the earliest days, but you are part of the lineage. The early rings teach the discipline required for the later ones. They teach that precision is not optional. They teach that stability is a daily accomplishment. They teach that the most advanced science in the world still depends on someone noticing a needle drift at 3 in the morning, which is, honestly, a very human way for the universe to be understood. And as the run continues, you keep doing what you do, checking, correcting, recording, while the detectors keep translating invisible events into pulses, and pulses into counts, and counts into paper. For now, the beam is alive, and the room is steady. So you sit in the hum, and you watch the quiet work continue, one ordinary event at a time. And the ordinary events have a strange texture when you stare at them long enough, because each one is a tiny compromise between chaos and bookkeeping. You watch the counters climb, and you remember that an event is not a single thing. It is a small cascade of hardware decisions. A pulse crosses a threshold. A discriminator decides it was real enough. A coincidence unit decides it was timely enough. A scalar decides it was worth remembering. And then, finally, a pen makes ink touch paper. You are not watching particles. You are watching permission. The universe throws confetti, and your apparatus decides which pieces count as evidence. That is why the early days feel so physical. The signals are not abstract numbers on a clean screen. They are voltages in cables. They are small currents in photomultipliers. They are warm racks humming in the corner, and every piece of it has a personality, which is a polite way of saying it can misbehave in a way you will only learn by suffering through it. The detector rates are steady tonight, which means you have time to notice the small practicalities, like dead time. Dead time is a phrase that sounds poetic, but it is brutally literal. It is the time your electronics spend being busy after an event, unable to register the next one, like a clerk who must stamp a form and cannot stamp the next form until the ink pad recovers. If the event rate gets too high, you do not count more, you count less accurately. So in early operations, you learn to keep one eye on the rate and one eye on the system's capacity. You do not just want more counts. You want counts that represent reality, not your electronics choking politely. And because you are human, you make this decision with a kind of tired morality. You lower beam intensity sometimes. You widen thresholds. You slow the run. You trade speed for honesty. Somewhere, someone impatient will ask why you did not push harder. You could answer with a lecture about systematic error. Or you could answer with the simpler truth, because the machine is not a wish-granting well, and you cannot bully it into giving clean data. You learn this especially when you look at the paper plots in the morning light and realize that a beautiful smooth curve can hide a very ugly problem. A drift in gain, for example. Photomultipliers are wonderful and also needy. Their gain depends on high voltage, temperature, and the subtle aging of surfaces inside. If the gain drifts, your pulses change height. If your pulses change height, your discriminator threshold begins to cut the world differently. You think you are counting particles above a certain energy, but you are actually counting particles above a threshold that is quietly sliding. So you calibrate. In the early days, calibration is not glamorous. It is test pulses injected into electronics. It is radioactive sources placed near detectors. It is running known reactions, known peaks, known lines, so you can say, this is where reality should land on our scale. And you do it again and again, because nothing stays put. Nature is consistent. Your equipment is aspirational. The irony is that the more sensitive your detector becomes, the more you must baby it. A very sensitive system is like a very expensive microphone. It hears everything, including the bad cable, the loose connector, the vibration from someone slamming a door down the hall. So you handle the whole arrangement gently. You route cables carefully. You label them. You tie them down. You keep them away from power lines when you can, because electrical noise loves to sneak into signal lines like gossip into a quiet room. In early experimental halls, cable management is a kind of folk art. It is bundles of coaxial cables draped over racks. It is handwritten tags. It is someone insisting, quietly, that this line must never be moved, because it took them 4 hours to get the timing right, and they would rather not do that again. Speaking of timing, you start to appreciate how ridiculous it is that you can measure anything at all. The particles in the ring are making laps, and depending on the machine, they are doing it in microseconds. Your detectors are responding in nanoseconds. Your logic is deciding in nanoseconds, and your record of it, your human record, is a pen scratching on paper at a speed that would embarrass a snail. And yet it works, because you do not need to capture the entire dance in real time. You only need to count and categorize carefully. You only need enough information to build a distribution. That is the secret comfort of statistical physics. You can be slow as long as you are consistent. So you listen to the tick of the monitoring speaker. Tick, 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 like rain on a window. Sometimes the tick becomes a quick rattle and you glance over, checking whether the rate is rising too high. Sometimes it slows and you feel that mild suspicion again, the sense that something shifted. Not panic, just attention. You check the beam current. Still steady. You check vacuum. Still deep and calm. You check the magnet currents, the ones that should be quiet and unchanging. Still fine. So maybe the detector is drifting. You call over to the experimental hall, or you pick up the phone and ask, softly, if they changed anything. A pause, a muffled conversation, then a reply. They moved a scintillator a few millimeters to improve acceptance. Acceptance is another gentle word for a brutal idea. It is the fraction of real events your apparatus can actually detect, given its geometry and thresholds. You could have the perfect accelerator, the perfect physics, and still miss most of reality because your detector simply does not cover the angles where the particles go. So experiments become a game of capturing as much as you can while knowing you will never capture all of it. You adjust and you measure and you correct for what you miss with simulations and careful reasoning. But in the early days, simulations are not as easy. Computing exists, but it is not on your desk. It is a shared resource, a distant room full of machines, punch cards, and waiting. So you rely heavily on geometry, on analytic approximations, on clever experimental design. You place detectors where the interesting particles are likely to go, and you accept that you are always peeking through a keyhole. The universe, vast and indifferent, reduced to what fits through your keyhole. There is something almost comforting about that limitation. It keeps you humble. It keeps you from believing you are seeing the whole truth. You are seeing a slice, and you are trying to infer the loaf. And when you hold a plot and see a small bump, you remember that the bump is not the bump. The bump is your detector's bump-shaped perception of the universe's bump-shaped behavior. That is why early papers and early internal notes are full of corrections. Efficiency corrections, acceptance corrections, dead time correction, pile-up correction. When two events happen too close together and the electronics merge them into one messy lie, it is not romance. It is accounting. But it is accounting with reality, which is the only client that never negotiates. While the run continues, you watch the small rituals around the control room and the hall. Someone checks the high voltage crate, reading out numbers and comparing them to a handwritten list taped to the rack. Someone else adjusts a threshold, then taps the panel lightly, as if reassurance helps. And you, on the accelerator side, keep the beam as boring as possible. Boring is the highest compliment you can give an operating accelerator. Boring means stable orbit. Boring means the vacuum does not creep upward like a slow fever. Boring means the radio frequency stays locked and the beam stays bunched, turn after turn, obedient to a field you never touch. You begin to sense, over the years, how much of the early culture was shaped by this craving for boring. People imagine discovery as fireworks, but the real enabling condition is monotony. The best run is the one where nothing forces you to improvise. The best night is the one where your logbook has the same sentence repeated. Stable, 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 with only minor corrections. It feels almost like cheating, except it is the hard-won reward of countless nights that were not stable. And that is why when CERN grows and rings become bigger and teams become more formal, the spirit remains the same. Bigger machines are not louder emotionally. They are simply longer, colder, more complex versions of the same discipline. You can feel that lineage in the way older operators talk. They speak with a calm fatalism. They do not say if something goes wrong. They say when. And then they list the likely failure modes the way farmers list weather patterns. Power supply trips, vacuum leak, radio frequency dropout, cooling flow issue, magnet interlock, a sensor lying for attention. The only question is which one chooses you tonight. And as you sit there, you start to understand how the lab itself had to change just to keep up with the machines it was building. In the early years, a lot of knowledge lived in people's heads and in thick logbooks. As the scale increased, the lab had to become more systematic. Procedures became printed. Settings became archived. Change control became a thing that people grumbled about and then quietly appreciated after it saved them from repeating a mistake. You cannot run a giant ring on folklore alone. You can try. The machine will punish you. So documentation becomes part of the accelerator. The written word becomes a component. The shift handover becomes a formal ritual because it is how you carry context across tired brains. You begin to see the control room as a living memory device. The panels remember through their settings. The logbooks remember through ink. The people remember through stories. And each form of memory has its own failure modes. Knobs can be bumped. Ink can be unclear. Stories can be wrong. So you cross-check. Always cross-check. This is the hidden personality of experimental physics, not the mythology of genius, but the reality of redundancy. Now and then, as the night drifts on, you get a call from someone more theoretical, someone who is not in the control room often. They ask, gently, how stable the energy is. They care because their analysis assumes a certain beam energy spread. And if that assumption fails, their beautiful equation will become a decorative object. Energy stability in an accelerator is not just about how hard you push the particles. It is about how uniform that push is. The radio frequency system creates buckets, little stable regions in phase space, where particles can ride. If particles get too far ahead or behind in phase, the field pushes them back toward the stable point. That is phase focusing. And it is one of the quietly elegant tricks that makes circular accelerators possible. Without it, the beam would smear out around the ring like impatient people spreading along a hallway. With it, the particles bunch and stay bunched, like a disciplined group that keeps finding its center. But the bucket has a size, and the beam has an energy spread. And if you are not careful, your beam can spill out of the bucket. It will debunch, and then your detectors downstream, synchronized to the bunch timing, will see the world differently. The whole experiment will shift its rhythm. So you keep the radio frequency locked. You watch the phase. You watch the amplitude. You watch for the signs of an impending unlock, which is often not dramatic. It is a gentle loss of capture, a widening of signals, a rise in beam loss monitors. Beam loss monitors are the accelerator's way of admitting embarrassment. They detect radiation from particles hitting the walls. They are like smoke detectors for invisible mistakes. In early machines, beam loss monitoring exists, but it may be cruder. Still, you learn to respect it because a loss is not just a loss. It is a cause. It can outgas the vacuum chamber, degrading conditions. It can activate components, making the tunnel a little less friendly. It can heat a spot. It can ruin an experimental run. So you treat beam loss like you treat a small leak in a boat. Not fatal immediately, but never something to ignore. And in the back of your mind always is the larger scale reality: radiation. Not the dramatic green glow people imagine, but the sober fact that when high energy particles hit matter, they produce showers of secondary particles. Some are harmlessly absorbed. Some penetrate. Some activate materials, creating radioactive isotopes that will linger. In the early days, the culture of radiation protection is developing. It exists, but it is learning. People are discovering, sometimes the hard way, where hotspots form, how activation builds, what components become unpleasant to touch after a long run. So, you follow procedures, You respect interlocks. You do not open doors when the beam is on. You do not bypass safety systems because you are impatient. Congratulations. You have discovered the easiest way to shorten your career. A good accelerator lab is full of interlocks, systems that enforce safety with cold indifference, doors that trip beam if opened, keys that must be carried, lights that indicate beam permit status, warning horns that sound before injection, giving anyone in the tunnel time to leave. It can feel excessive until you remember that the beam does not care if you are in the way. The beam is tiny, but the showers it can generate are not, and your body is not designed to be a detector. So the night shift has a certain quiet respect built into it. You do not fear the machine in a panicked way. You fear it in a grown-up way. You follow the rules because the rules are written in the language of consequences. And then, because this is still a human place, someone will tell you a story. A story about an early mishap, not a catastrophe, but a lesson. A door interlock that failed once. A beam that was accidentally dumped in the wrong place, activating a component unexpectedly. A technician who found a warm spot on a beam pipe that should never be warm. These stories become part of the lab's folklore, but they are not superstitions. They are training. They teach you where the machine's indifference becomes personal. As the world above continues turning toward morning, you get a sense of the lab's expansion over time and how the early days planted habits that later machines depended on. When you move from smaller rings to bigger ones, you do not abandon the old lessons. You amplify them. A small drift in a small ring can be corrected with a knob and a note. In a larger machine, a small drift can involve many systems. It can require coordinated changes. It can require feedback loops, automatic systems that sense beam position and apply corrections continuously. Feedback is the machine learning to babysit itself. But even feedback has to be tuned by humans, and the humans still sit in a control room at night, listening for the subtle signs that the automatic system is making things better or making things worse very efficiently. Early CERN culture, with its calm troubleshooting and obsession with stability, becomes the foundation for all of it, because the physics goals keep expanding. You want higher energy to probe smaller distances. You want higher intensity to see rarer processes. You want better detectors to distinguish signal from background. You want faster data acquisition because the event rates become too high for paper and patience. And each improvement creates new failure modes. Higher intensity means more collective effects. The beam can become unstable like a crowd that starts chanting in sync. Tiny perturbations can grow. Coupled bunch instabilities can appear. The beam can oscillate transversely, side to side, or longitudinally, in phase and energy. To tame that, you develop dampers, systems that sense oscillations and apply corrective kicks. You develop better vacuum to reduce ion-induced effects. You develop careful impedance control, smoothing the vacuum chamber geometry so wake fields are smaller. You do not need to understand the full math to feel the vibe. The vibe is simple. The beam is not just a thing you push. It is a thing that can develop moods when it becomes intense enough. And the machine, if you want it to be boring again, must become smarter, steadier, more controlled. So the lab becomes a place where engineering and physics are inseparable. It is not a physics temple with some machines in the basement. It is a machine temple where physics is the reason. That is why the people matter. You cannot operate an accelerator without a particular kind of collaborative temperament. Not saintly, just practical. People who can be tired and still careful. People who can disagree about settings without making it personal. People who can admit uncertainty and ask for help. Because a large machine does not reward lone heroes. It rewards teams that can keep their ego out of the signal path. And if you are lucky, you find a small coziness in this. Not because the lab is comfortable, but because it is steady. You know the faces. You know the voices. You know who to call when the vacuum gauge starts creeping, and who to call when the radio frequency refuses to lock, and who to call when a detector begins to sing in noise. In the early days, you can still recognize most people. Later, the lab becomes too big, but the shift crew remains intimate. A small group sharing a long night, keeping the machine honest. The coffee gets worse sometimes because scale does that. But the rituals remain. You check the same readings, you initial the same forms, you write the same kind of notes. Time, beam, current stable, vacuum stable, minor orbit correction at such and such time. And those notes, which feel boring now, will matter later. Because when an analysis shows something odd, the first question is not philosophical. It is operational. Was the beam stable? Was the detector stable? Was there a trip? Was there an intervention? So your handwriting becomes part of the scientific record. Your tired attention becomes a piece of epistemology, which is a fancy word for how we know what we know. You may not get your name on the plot in a paper, but you are in the plot's integrity. That is the quiet dignity of operations. Now, as you sit in this hum, you can let your mind drift gently into the particles again, because there is still a strange comfort in their consistency. Particles, despite the weirdness of quantum mechanics, obey symmetries. They obey conservation laws. They do not make exceptions for holidays. And the most soothing part is that you can predict them statistically. You can say, if you run long enough, you will see this many of that. Within uncertainty, you can plan an experiment around expectation, and the universe will either comply or it will show you where your expectation was wrong. Either outcome is information, which is why the Accelerator is such an honest machine. It does not create truth. It creates conditions where truth can be measured, and as the lab scales up, the questions become more ambitious. In early days, you might be studying scattering, measuring how often particles bounce at certain angles. You might be producing pions and kaons and seeing how they decay. You might be exploring resonances, short-lived states that appear as bumps in invariant mass distributions. Invariant mass is one of those phrases that sounds like it should be carved into a marble pillar. But it is just a clever accounting of energy and momentum. You take the measured energies and momenta of decay products, and you compute a value that should match the mass of the parent particle, regardless of how fast it was moving. It is a way to identify invisible parents from visible children. And in the early days, those parents are discovered not with fireworks, but with patience. A bump appears, it repeats, it sharpens with more data, it survives calibration checks, and then, slowly, it becomes real. But you do not feel that in the moment. On shift, you feel the machine and the routine, the hum, the occasional phone call, the small adjustments, the mild satisfaction of steady conditions. And if you are unlucky, you feel the opposite. A trip. It happens with a sound that is almost insulting in its simplicity. A relay click, a light changing state, a fan changing pitch. The beam permit drops. The beam is gone. The detector ticks fade, not because the universe stopped, but because your controlled source stopped. Someone sighs. Softly, someone stands up. The room becomes a little more awake. You look at the fault panel. In early rooms, this might be a literal panel of lights, each one corresponding to a subsystem. One light is on, or a few. It is never as clear as you want, but it is something. You call it out. Radio frequency fault, maybe. Or magnet power supply. Or vacuum interlock. Or cooling. You write the time. And then you begin the calm recovery dance. You check the obvious. Has the main power tripped? Is there a breaker? Is the cooling flow okay? Did the vacuum spike? Sometimes the fault is real. A component overheated. A sensor detected a condition that would damage equipment. The interlock did its job. Sometimes the fault is false, or at least not dangerous. A sensor glitch, a contact bounce, a relay that is old and dramatic. In early days, you learn to distrust the binary clarity of fault lights. The world is analog, and your fault system is trying to compress it into yes or no. So you verify. You check temperatures with a handheld meter. You check currents. You check whether a pump is actually running, not just whether the indicator claims it is. You become, again, a detective in a concrete tunnel. If the beam is off, you may have time for access, depending on procedures and radiation conditions. In some cases, you can go into the tunnel. In others, you wait. Waiting is a big part of safety. You let radiation levels decay. You respect cool-down periods. You do not rush, because rushing is how you touch the wrong thing. So you sit, again, in the control room, now listening to a slightly different hum. No beam, but still power, still pumps, still fans. The machine is never fully asleep, even when it is not running. You make a call to the on-call expert. They answer with that tone that says, yes, they were sleeping, and yes, they expected this. You describe the fault. You read the relevant numbers. You do not editorialize. You do not guess loudly. You just report. They ask for one more measurement. You take it. They ask if you try to reset. You have not, because you were waiting for permission, because that is part of the culture. You do not reset blindly. You want to know what you are resetting. They tell you to reset, but only after checking one condition. You check it. It is fine. You reset. Sometimes it works, and the fault clears like a bad mood passing. Sometimes it does not, and the expert tells you they are coming in. So you wait, and you keep notes, and you keep the room calm. When they arrive, they do what experts always do. They look at one thing you did not look at, and it is embarrassingly obvious in hindsight. They pull a connector, reseat it, and the fault clears. Or they notice a cooling valve half closed. Or they see that a timing module is drifting, and they swap it. These are not cinematic interventions. They are small acts of maintenance performed in the middle of the night by someone who has done it before. And then you restart the process. You bring systems back online. You pump down if needed. You condition the radio frequency cavities, gradually increasing power so they do not spark. You ramp magnet currents carefully, because magnets and power supplies have their own preferences about being woken up. Conditioning is one of those quiet accelerator words that means you are teaching hardware how to behave under stress. Radio frequency cavities in particular are temperamental. They hold strong electric fields that push the beam. In vacuum, high fields can cause breakdown, little discharges. So you condition them by increasing power slowly, letting surfaces clean up, letting microscopic protrusions burn away, letting the system become comfortable at higher gradients. It is like breaking in new shoes, except the shoes can arc and trip your machine. So you do it patiently, and when the beam returns, when injection works, when you see the circulating current again, you feel that soft relief that comes from restoring a fragile order. Not joy, just relief. You look at the clock, you make a note, you call the experimenters and tell them beam is back, stable enough for now. They will restart their run, their counters will climb, their plots will grow smoother, and you will sit again in the hum. This cycle, stable run, fault recovery, stable run, is the heartbeat of accelerator life, especially in the early days. It is why the job feels both monotonous and oddly intimate. You are not just operating a machine, you are living with it, learning its habits, its weaknesses, its nightly moods. Now, as CERN grows, the machines become bigger, and the consequences of faults become larger. A superconducting magnet quench, for example, is not just a minor inconvenience. It can dump enormous stored energy into heat and protection circuits. It can require hours to recover, to cool down again, to reset systems. So the lab invests heavily in reliability, in redundancy, in better diagnostics, because downtime is expensive and science is impatient. But even with modern systems, the old truth remains. When something goes wrong, it often goes quiet first. The early days trained people to hear that quiet. Now, somewhere in the lab's timeline, you begin to see the transition from those early manual days into something more automated. Not overnight, never overnight. It comes in layers. At first, it is better instrumentation, more beam position monitors, more precise current transformers, more reliable vacuum gauges. Then, it is better control systems, computers that can record data continuously, display trends, issue alarms, and then, eventually, you get feedback loops that can keep the orbit centered without you turning a knob every few minutes. In the early days, you are the feedback loop. In later days, you supervise the feedback loop. This changes the feeling of the shift, but it does not eliminate the need for you. It changes your role from constant manual steering to higher level oversight. Instead of watching one needle, you watch trends, you watch correlations, you watch whether the automatic system is chasing noise or correcting real drift. And you still keep the logbook, though now it might be electronic, and it might timestamp your entries automatically. But you still write, because context is not something a sensor can fully capture. The sensor can tell you the vacuum rose. Only you can tell it rose right after someone opened a door, or right after a thunderstorm caused a power flicker, or right after a maintenance team tightened a flange. Humans are still the best sensors for stories. And stories matter, because the lab is a long-term organism. It spans decades. People come and go. Hardware changes. Procedures evolve. But the machine's history remains relevant. Because old decisions leave traces in metal, in cable routes, in the way a system was designed to cope with limitations that no longer exist. So you see older engineers walking the tunnel, looking at a new installation, and you can tell they are reading the past in the present. They see why a component is where it is. They remember the constraint that forced it. They know the workaround that became standard. In a place like this, the past is always in the wiring. And that is why early CERN feels so important. Not because it was primitive, but because it set patterns. It trained people to value stability, to value careful measurement, to accept that progress is made of small, boring improvements, better vacuum practices, better magnet alignment, better power regulation, better timing distribution, better grounding and shielding. Each one is unglamorous. Together, they enable everything. And while you are sitting here tonight, you can almost feel that accumulation. The machine around you is a snapshot in a long evolution. It began with smaller rings, modest energies, manual controls, paper logs. It grew into bigger rings, stronger magnets, more automation. It became a global collaboration, not just a European one, because the questions became too large for any single institution. And through all of it, the core act remained the same. You create a controlled environment. You accelerate particles. You collide them. You detect what comes out. And you compare that to your expectations. And when the expectations fail, you do not yell at the universe. You check your equipment. Then you revise your understanding. That is the deal. Now, your mind, because it is human and sleepy, might drift back to the particles again. To keep things simple, protons and electrons in a ring, guided by magnets, pushed by radio frequency cavities. But there is a quieter, weirder point to remember. Even in a machine built to be classical and controllable, quantum behavior still leaks in, not just in the collisions, but in the beam itself. There is a concept called emittance. It is the measure of how spread out the beam is in position and angle, like how wide a pencil line is and how much it wiggles. Emittance is a beam quality. Low emittance means a tight, neat beam. High emittance means a smeary beam that will scrape and die. In a purely classical world, you could imagine making emittance arbitrarily small with perfect control. But in reality, there are limits. There are noise sources. There is scattering. There are quantum effects and synchrotron radiation for electrons, where emitting photons causes random kicks, leading to an equilibrium beam size. In electron machines, synchrotron radiation is a constant companion. As electrons bend in magnetic fields, they emit electromagnetic radiation. It is not optional. It is electrodynamics doing its thing. This radiation carries energy away, so radio frequency cavities must replenish it. The balance between radiation damping and quantum excitation sets the beam's equilibrium properties. In early proton machines, synchrotron radiation is negligible because protons are heavier. They do not radiate much when bent. But in electron synchrotrons, it is central. It becomes both a nuisance and a tool. A nuisance because it wastes energy and heats components. A tool because it damps the beam, making it easier to keep tight. And later, because the radiation itself becomes useful as a light source. That is one of the lab's quiet side stories. The same machines built to smash particles also became sources of brilliant light for studying materials, biology, chemistry. Synchrotron light facilities grew out of Accelerator technology like an unexpected branch. You build a ring to explore fundamental physics, and congratulations, you have accidentally built a microscope for proteins. Nature enjoys these crossovers, but in the early CERN night shift vibe, you mostly feel the radiation as something to manage, not something to celebrate. You manage shielding, you manage background in detectors, and you keep the beam stable. Now, because this is a bedtime story for the existentially curious, you might notice the emotional undertone in all this. You are spending your night maintaining a fragile thread of charged particles in a vacuum, guided by fields, kept coherent by feedback and discipline, all so you can learn something about what matter is made of. It is a very elaborate way to satisfy curiosity, and it works, which is the strange part. The universe is not obligated to be understandable. It is not obligated to yield to your methods. It could be messy in a way that refuses clean measurement. It could be unpredictable at the scales you probe. But it is not, at least not in that way. It is consistent enough that your careful, boring machine can extract answers. That consistency is both comforting and mildly unsettling, because it suggests that you too are a system running on laws you did not choose. Your neurons firing in patterns, your attention drifting, your fatigue building, your small decisions shaped by training and routine. You are not outside nature. You are a little piece of it, sitting in a control room, using one part of nature to interrogate another, and the whole thing is held together by coffee and documentation. There is a humility in that, a quiet one. And speaking of quiet, the night shift has a particular sound when the run is stable, a kind of layered white noise. Fans, transformers, pumps, the occasional clack of a relay, the faint chatter of low voices, the soft scratch of pen on paper. These sounds become the lab's lullaby, not because they are soothing in themselves, but because they signal that the machine is alive and behaving. You can tell when something changes, even before an alarm, because the soundscape shifts. A fan bearing begins to whine. A pump changes pitch. A rack stops humming. A relay starts clicking too often. Your ears become instruments, even if you pretend you are relying only on meters. Humans are good at noticing pattern changes in sound. It is one of our older survival skills, repurposed for vacuum pumps. So you listen, and as you listen, you might find yourself thinking about the early mornings when the shift ends and you hand over the machine to the next crew. The handover is its own ritual, and it is where the human chain becomes visible. You gather notes, you summarize events, you mention the small drift. You corrected, you mention the trip and the reset. You mention the detector rate change and the reason. You do not just hand over numbers. You hand over context, because the next crew will make decisions based on what you tell them. And you want them to make good decisions, because you do not want your night's work to unravel in the next hour. There is a quiet solidarity in that. Even if you do not know the next operator well, you are collaborating across time. Your notes are a gift to their tired future self. And in a way, that is how the whole scientific project works. You write things down so someone else can continue without starting from zero. You build a ladder of knowledge, rung by rung, boring rung by boring rung. Now, while we are still in the middle of this night, there is another aspect of accelerator life that you feel more than you read about in popular stories. Alignment. You might imagine that magnets are installed and then forgotten, as if their positions are obvious and permanent. But the ring is long. The tunnel is subject to temperature changes. The ground moves, slowly, imperceptibly, but enough over time to matter. Concrete creeps, supports, settle. Metal expands and contracts. Equipment shifts by fractions of a millimeter, and those fractions add up along the circumference. So, alignment teams are a quiet tribe in the accelerator ecosystem. They use surveying instruments, lasers, reference markers to ensure that magnets are where they should be and that the beam pipe follows the designed path. In early days, this is done with more manual methods, optical instruments, plumb lines, careful measurements. Later, it becomes more sophisticated, but the concept remains the same. You are building a track for particles that cannot see the track, and the track must be smooth enough that the beam does not constantly correct for bumps, because every correction is a potential source of loss and instability. So you keep the ring aligned as best you can, and when you cannot, you compensate with orbit correction magnets. Orbit correction is like steering around potholes you cannot fill. And you do it, again, with patience. In a control room, you might not think about alignment often until the day you cannot get a good orbit without using too much correction. Then you suspect something has moved. Then you call the alignment crew. Then you learn that yes, a support settled, and a magnet is off by a small amount. Small to a human. Significant to a beam. So you schedule an intervention. You shut down. You enter the tunnel. You loosen bolts. You jack up a heavy magnet by a fraction. You tighten. You remeasure. It is slow, physical work done under fluorescent lights in a tunnel that smells like dust and metal and old air. And then you return to operation, and the beam behaves better, and nobody outside the lab will ever know that progress sometimes looks like turning a wrench 1/8 of a turn. That is the reality behind the clean plots. Now, the outline of your night and of this whole story is still moving forward. The early days to bigger rings, the calm sense of scale, the soft look at particles without the math. You have already tasted those themes, but there is more texture to add, because scale is not just size. Scale is the way small imperfections become large consequences when the machine grows. A bigger ring means more magnets, more power supplies, more vacuum joints, more opportunities for a single weak link to ruin your night. So, reliability engineering becomes central. You design systems with redundancy. You monitor more parameters. You build predictive maintenance schedules. You replace components before they fail, if you can afford it. And you still inevitably get surprised, because complex systems always find the one failure mode you did not anticipate. That is why the control room is never purely automated. There is always a human in the loop, because humans are good at improvising when the model fails. Not always good, but good enough to keep the machine safe. So you remain here, tonight, as a kind of guardian, not a hero, more like a night watchman for an invisible river. Now, one of the more quietly strange parts of accelerator life is how the beam, when it is stable, becomes almost boringly obedient, and then you remember that it is made of quantum objects. Each proton is not a tiny billiard ball. It is a quantum excitation of a field with internal structure, with quarks and gluons swirling, with probabilities that govern how it will interact. And yet, as a beam, it behaves like a current in a wire. You measure it in milliamps or in number of particles per bunch, and you steer it with magnets as if it were classical. This is one of the practical miracles of physics. When you have huge numbers of particles, the collective behavior becomes smooth. Quantum uncertainty averages out. The beam becomes a fluid. So you can treat it with the mathematics of optics, describing beta functions, and focusing like light rays through lenses, even though there are no rays and no lenses in the human sense. Quadrupole magnets are lenses for charged particle beams. They focus in one plane and defocus in the other. And by alternating them, you create net focusing in both planes. It is called strong focusing. And it is one of the key innovations that made modern synchrotrons practical. Without strong focusing, machines would need much larger apertures, much bigger magnets, much more cost. With strong focusing, you can keep the beam tight using alternating gradient focusing, like a sequence of lenses that squeezes in one direction, then the other. It is an elegant trick, and it is also why the beam optics vocabulary feels like a hybrid of accelerator jargon and camera shop terms. Beta function, phase advance, chromaticity. Chromaticity is not about color here, but it is a borrowed metaphor. It describes how the focusing depends on particle momentum. Particles with slightly different energies see slightly different focusing strengths. This can cause the beam to spread, to become unstable. So, you correct chromaticity with sextupole magnets, another layer in the magnetic chorus. Each magnet type adds a harmonic to the ring's field. Dipoles bend, quadrupoles focus. Sextupoles correct chromaticity. Higher-order multipoles correct higher-order errors, sometimes intentionally, sometimes as a necessary evil. And the beam, sensitive and indifferent, responds to the sum of it all. So, in the early days, much of your time is spent learning the ring's optics. In a practical sense, not just the theoretical design, but the real implemented machine. The one with alignment errors, field imperfections, hysteresis in magnet iron, power supply ripple. Hysteresis is another one of those words that sounds philosophical. In magnets, it means the field depends on the history of how you ramped the current. Iron remembers. So, when you set magnet currents, you cannot just go to a number. You have to follow a procedure. You degauss or you ramp up and down in a prescribed way so the magnet lands in a reproducible state. You are not just setting values, you are guiding a system with memory into a consistent mood. That is why early operations are full of rituals. They are not superstition. They are practical ways of managing hardware that has history. And while you are managing that, the experimenters are managing their own rituals. Calibrations, threshold checks, gas flow checks for wire chambers, temperature stabilization, high voltage ramping. Wire chambers, in particular, require gas, and gas systems are their own quiet world. Mixtures of argon, methane, carbon dioxide, sometimes more exotic, flow rates, pressure regulation, purity monitoring, a gas mixture that drifts changes detector gain and timing. So gas people, become essential. They are the keepers of invisible atmospheres inside detectors, just as vacuum people are keepers of invisible emptiness inside the beam pipe. It is all invisible management. You might notice a theme. And speaking of invisibility, there is also the matter of beam diagnostics, the tools you use to see the beam without killing it. Beam position monitors, as mentioned, can tell you where the beam is in the pipe. There are different types, but often they are electrodes that pick up signals induced by the passing bunches. The relative signals tell you the beam's offset. Beam current transformers measure beam intensity by sensing the magnetic field of the circulating beam, like a clamp meter around a wire. Except the wire is a bunch of protons in vacuum. There are wire scanners and screens and foil monitors, but those are invasive. They intercept the beam, producing signals, but also disturbing it. In early operations, you often use invasive diagnostics during setup, then remove them during data taking. Because if you touch the beam too much, it stops being the clean probe you need. So you learn to rely on non-invasive monitors when possible. And you learn the art of making a beam visible indirectly by its subtle effects on circuits, on induced voltages, on radiation monitors. It is a kind of remote sensing, like listening to a creature in a dark cave by the echoes of its footsteps. Now, because you are still awake in this story, and because the night is long, your mind might ask a softer question. Why does any of this matter? Not in the dramatic sense, not in the funding pitch sense, in the quiet, existential sense. Why do humans build machines like this? Part of the answer is simple curiosity. We want to know what matter is, how forces work, why the universe has the structure it does. But another part is less noble and more human. We build accelerators because we can, because we learned how to control fields and vacuum and timing well enough to make an invisible river behave. It is an expression of competence, and competence is soothing in a world that often feels chaotic. So the control room, in a strange way, is a sanctuary of predictability. The universe may be indifferent, but it is rule-based. The machine may be sensitive, but it is understandable. Your actions have consequences you can trace. In daily life, consequences are often delayed and ambiguous. In an accelerator, if you turn the wrong knob, you will know. That clarity, harsh as it is, can be comforting. Of course, it can also be humiliating, because the machine will reveal your mistake instantly, without politeness. But you learn, and you get better, and the machine becomes more boring, and boring becomes a kind of peace. Now, as the hours slide, and you keep the ring stable, the story naturally drifts toward scale again, toward how bigger rings change the culture and the technology. When you get to a machine, like the Large Hadron Collider, for example, you are no longer dealing with warm iron magnets. You are dealing with superconducting magnets operating at temperatures colder than outer space. Liquid helium, superfluid helium, cryogenic plants, quench protection, energy stored in magnets like a coiled spring, waiting. The stored magnetic energy in a large superconducting ring is enormous. It is not something you casually ignore. It is a sleeping dragon made of inductance. So the procedures become stricter, the interlocks become more layered, the control room becomes more sophisticated, and still, someone is on shift at 3 in the morning, noticing a small drift, They might be noticing a quench precursor signal, a slight change in voltage taps across a magnet, or a small pressure change in a cryogenic line, or a subtle orbit drift, corrected by feedback, but trending. The details change. The posture remains. That is continuity. And continuity is the real quiet magic of CERN. It is not just a place. It is a multi-generational project of learning how to operate complex machines reliably so that physics can be done with trust. Trust is the key word. You cannot do precision physics without trusting your instrument. And an accelerator is an instrument, even if it is kilometers long and tries to kill you with vacuum and radiation and stored energy. So you build trust with routine. And routine is boring, which is why this story works as sleep content, frankly. The truth is repetitive. The machine runs on repetition. The data accumulates through repetition. Knowledge emerges from repetition. It is the same principle, over and over. Now, there is another quiet aspect to mention, because it affects how early accelerators feel compared to later ones. In early days, the control systems are local. You walk to a rack. You adjust a knob. You see the effect. The feedback loop includes your body. Later, control becomes remote, computerized. Settings are changed through software. The feedback loop includes networks and interfaces. This brings benefits, but it also introduces new failure modes. Software can have bugs. Network latency can confuse. A user interface can mislead. A remote operator can change a setting without feeling the physical reality of the hardware. So later labs develop strict controls, permission levels, change logs. In the early days, a knob's position is obvious. In later days, a setting is a number on a screen, and numbers can be changed too easily. So the culture adapts. It adds layers of procedure to replace the physical friction that used to protect the machine. Every era has its own version of keeping humans from being too human. And you, tonight, are living in the earlier era, where physicality is still close. The knobs have resistance. The switches have feel. The meters have needles. The paper has weight. You can sense the machine with your hands and ears. It is an intimacy modern systems often lose, even as they gain precision. Now, as the run continues and the beam remains stable, you might find a moment to walk again, to stretch your legs, to look at the ring's infrastructure. You take a corridor, and the air changes. Cooler, more dust, the smell of concrete and metal, and occasionally the sharp hint of ozone near high-voltage equipment. You pass racks of power supplies. They are large, heavy, and they emit heat. You feel the warmth on your skin as you pass, like walking near a radiator in winter. These power supplies are not glamorous, but they are crucial. They provide the currents that define the magnetic fields that define the beam's trajectory. If a power supply has ripple, the field ripples. If the field ripples, the beam's orbit wiggles. The beam might tolerate small wiggles, but it has limits. So power supply engineers work hard to reduce ripple, to improve regulation, to make current stable against line voltage fluctuations and load changes. In early days, this is done with analog control circuits, with careful design, with big components, with the kind of engineering that smells faintly of hot insulation. Later, power electronics improve, switching supplies, digital regulation, better sensors, but the goal remains the same: make the current boring. You pass a cooling manifold, pipes branching like a metal tree, water flows through. You can hear it, a steady hiss and occasional gurgle. You check for leaks. You look for condensation. You look for signs of corrosion. Corrosion is slow, but it is relentless. Water plus metal plus time equals trouble. So maintenance is constant. In a facility like this, maintenance is not an interruption to science. It is part of the science. Without maintenance, nothing works long enough to measure. You pass a vacuum pump station and you hear the low thrum. Vacuum pumps come in types: mechanical roughing pumps, turbomolecular pumps, ion pumps, cryopumps in some contexts. In accelerators, you often use a combination. Roughing pumps bring pressure down from atmosphere. Turbos pull down further. Ion pumps maintain ultra-high vacuum by ionizing residual gas and burying it in electrodes. Ion pumps are quiet and elegant. They have no moving parts. They are like little electric traps for molecules. They sit along the ring, maintaining emptiness with steady voltage and a kind of patient appetite. In early days, ion pump technology is already present, but it is still developing, still being understood. You learn that vacuum is not one thing. It is a system. It is pumping speed, conductance of pipes, outgassing rates, leak rates. It is the art of making almost nothing continuously. And as you walk, you see how the lab is a layered organism: electrical distribution, cooling, vacuum, magnet power, radio frequency, control, diagnostics. Each layer supports the next. If one layer fails, the layers above it become irrelevant. So operators learn to respect the boring layers. You cannot accelerate particles without water. This is one of those truths that would disappoint anyone expecting science fiction. Now, you return to the control room, and the hum welcomes you back. You sit and you check the readings again, because routine is comfort and also vigilance. Beam, current, stable. Orbit, stable. Vacuum stable. Detector rates stable. It is one of those blessedly boring periods, so your mind drifts again toward the soft look at particles without the math, because that is part of the charm of this job. You guide particles with fields, and you measure their interactions, and you build a model of reality. But what are particles? In the simplest human sense, they are excitations. They are quantized bits of fields. They are patterns that persist. An electron is not a tiny ball of stuff. It is a stable pattern in the electron field, carrying charge and mass and spin. Spin is another word that misleads. It is not literally a little ball spinning. It is an intrinsic quantum property, a kind of built-in angular momentum, with no classical analog that fully captures it. But the word spin stuck, because humans like metaphors, even when metaphors lie. Particles also have wave behavior. They have wavelengths. They interfere. They diffract. They have probabilities. In an accelerator, you might not feel that wave nature directly because the beam is treated classically, but the collisions reveal it. The cross-sections, the scattering amplitudes, the resonance shapes, they are all quantum. So you live in this hybrid world. You steer beams with classical electromagnetism. and you interpret interactions with quantum field theory. It is like driving a car using Newton's laws, then analyzing the engine with quantum chemistry. Different layers of reality cooperating, and that cooperation is itself a comfort. It suggests the universe is not arbitrary. It is layered, but consistent across layers. Now, one more quiet piece of Accelerator life, especially in early days, is how much of the work is about knowing what not to do. You do not make big changes during a stable run. You do not tweak multiple knobs at once. You do not chase noise. You do not assume a gauge is telling the truth without confirmation. You learn to be conservative because you are responsible for something fragile. This conservatism can feel almost like superstition, but it is rational. It is learned through loss. Every operator has a memory of a time they made a change that seemed harmless, and the beam vanished instantly, leaving them staring at a flat line. That memory becomes a constraint. So the job shapes your psychology. It trains patience. It trains you to respect small effects. It trains you to accept that sometimes the best action is no action. That is not a common lesson in daily life. In daily life, people reward activity. They reward the appearance of doing something. In an accelerator control room, doing something unnecessarily is how you ruin everyone's night. So you learn to sit still, to watch, to wait. It is a discipline. And in the calm moments, when you are not troubleshooting, you can hear the long arc of the lab again. The early days, with paper logs and dials, leading to bigger rings, leading to more automation, leading to massive collaborations, leading to questions about fundamental symmetries, particle masses, forces, all of it built on the same idea. Keep an invisible beam stable enough to ask a clean question. Now, the night is still moving, and there is more to say, but the machine remains stable for the moment, and stability gives you the luxury of reflection. So you glance at the logbook, and you notice how thick it has become. Each page is a night. Each line is a small intervention or a note that nothing happened. Each initial is a human briefly present, keeping the machine honest. If you flip back far enough, you can see how the machine matured. Early pages might be full of faults, trips, interventions. Later pages might be calmer, more repetitive, because the system improved. Or the opposite. If the machine aged and grew temperamental, machines, like people, have life cycles. They start new and awkward. They become reliable. They age. Components wear. Obsolescence creeps in. Spare parts become rare. People who knew the original design retire. Then a decision is made: upgrade or retire. And CERN, like any lab, is always balancing those decisions, building new while maintaining old, learning while operating. It is a living compromise, and you, tonight, are one of the small hands keeping the compromise working. The beam is still there. The detectors are still counting. The plots will still print. So you keep watching, because that is